In this video, I'm going to be solving the June 2025 question 5. So the question reads, a Sphere construction company has just completed a skyscraper building with 15 stories, and it hands it over to Shatek Engineering. So Shatek CEO decides that not all stories should be accessed by the customer as it is its head office. Therefore, he gives a restriction to certain levels. Okay. You as a programmer, you are subcontracted to come and program a lift such that it opens only on the floor on the following levels that are open to the public, such as ground. Okay, so the floors that are open, okay, let's say open floors. So we're going to say open floors. So open floors, we have the ground, which is equivalent to floor 0. Then we're going to say 1, 3 is also supposed to be open, 6, 8 is supposed to be open, 13 and 14 they are also supposed to be open. And so it says, after you program the lift, draw the logic circuit that will respond to the program you fed in the lift. Test the lift by means of a truth table if it's corresponding to the program. Okay, so we draw the truth table, then we come up with the Boolean expression. Then from the Boolean expression, we draw the logic circuit. So the way we go about this, so we know that the floors are going up 14. So that means that the number of rows on a truth table are going to be what? More than 14, or they're going to be 14. So once you see a number that your floors are above 8 already, you will know that we are going to be working with a hexadecimal BCD table. Okay, so our truth table is going to count from 0 to 15, which means we're working with hexadecimal, right? So we're going to say here, I'll say floors. Okay, then here I'm going to say input A, input B, input C, and input D in output X. Okay, so I'll say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, say 10, 11, 12, 13, 14, and 15, like this. Okay, so I'm going to, so I will demarcate like that. So just a normal usual way that you draw a truth table. I'm going to close this also. So this is just showing us the number of floors. Then these are our inputs, this is our output. So then these ones I'll demarcate like this. This one I'll demarcate like this. This one I'll demarcate like this. The first one I'm going to have 8 zeros and 8 ones. Okay. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3. So just quickly do this. Then 4 zeros, 4 ones, in 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, then 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. Okay, so now here we're going to have the number of, we're going to look at the number of floors that are open, as the question has said. So the ground floor is going to open, so we put a 1 here. Okay, the third floor is going to be open, so we put a 1. So the 6th floor is going to be open, so it's active, we put a 1. 8 is going to be open, we put a 1. 13th floor is going to be open, so we put a 1. And then 14th floor is going to be open, we put a 1. So you say 0, 0, 0, 0. The remaining floors are closed. There's a 0 everywhere, like this. So now that we have this, so this is how our truth table is going to be. So you write a 4-input BCD table. Why I'm not using 3 inputs is because for you to figure out the number of rows you're going to have in a truth table, use the formula 2 to the power n. N meaning the number, we say 2 to the power n, where n means the number of inputs. So if we say 2 to the power 3, we're going to have 8. If we say 2 to the power 4, we're going to have what? We're going to have 16. So in this case, we're using a 4-input truth table because the number of floors count up to more than 8. Okay, so that's how we came up with this truth table. So then you put ones where the floors are going to be open and zeros where the floors are going to be closed. So the question further says that we need to draw the logic circuit for the lift. Okay, so the only way we can draw a logic circuit is first of all by finding the Boolean expression for the output. So to do that, we're going to need to use a Carnot map. So to do the Carnot map, a 4-input Carnot map, so A, B, C, a 4-input Carnot map, I'm going to say we have A, B this side, we have C, D this side. Okay, then I'm going to draw like that. And okay, so I'll say set we have 0, 0, 0, 1, 1, 1, and 1, 0. Inside we have 0, 0, 0, 1, 1, 1, and 1, 0, like this. Then we'll close like that. Okay, so we'll start. So you check the number of inputs that you have that are less. So we have 1, 2, 3, 4, 5, 6. So we have the ones are less. Okay, so I'm going to use the ones to put into the Carnot map. If the zeros were less, I'd have used the zeros, find the equation for the zeros, and invert it to find the equation for the bit. So I'll start with this first one here. This first one is on 0, 0, 0, 0. So 0, 0, 0, 0. This is where the first one is. So I'll put this one. This one I have 0, 0, 1, 1. So 0, 0, 1, 1. The one is here. Put this one. Then I have this one here. This one actually lies on this one lies on 0, 1, 1, 0. So 0, 1, 1, 0. So it's here. Okay, this one here lies on is in the box 1, 0, 0, 0. So 1, 0, 0, 0. It's there. Okay, and this one lies on 1, 1, 0, 1. 1, 1, 0, 1. 1, 1, 0, 1. It's here. You can set this one. So this one lies on 1, 1. Oh, this one lies on 1, 1, 0, 1. 1, 1, 0, 1. Yeah. Then this one lies on 1, 1, 1, 0. So 1, 1, 1, 0. 1, 1, 1, 0. It's there. Okay, so we have inserted all the ones, so I'm going to focus on the Carnot map. So meaning the remaining boxes are what are representing zeros. Zeros that are in the truth table, in the output here. Okay, so here we can make the possible pairs that we have. So we can pair these two. I think that's the only pair that we can have. Round column at the far ends we have nothing. So we'll start with the pair. So we're going to say the equation or the Boolean expression for x. We start from the pair itself. So here it is 0, 0, 0, 1, 1, 1. So 1 is common here, so I'll take b. B, then this side we have c and d bar. Okay, plus we go to this one here. This one is going to be a bar, b bar, c, d. So I've insert this one, then this one is going to be a bar, b bar, c bar, d bar, plus so we insert this one here. So then you go to this one. This one is going to be a b. It's going to be a b, then c bar d, plus this one here is going to be a, then b bar, a b bar, and then c bar d bar. So you may ask to say, you may be aware of how to use a Carnot map, then you're going to say, why am I putting bars? So once you see a bit like this bit here, 0 is representing a and b is, and this is the first 0, 0. This bit is representing a, this one b, this one a, this one b, this one a, this one b, this one a, this one b. This side, this one is c, this one is d, c, d, c, d, c, d. So wherever I'm inserting these bits in a Boolean expression, wherever you see a 0, you have to put a bar on top of that letter, and wherever you see a 1, you don't put a bar. Okay, so like in the case of, let's say, this one, so a here is a 1, so it's the 1 without a bar. Then b is represented by 0, so it's b with a bar. Then if you go this side, we have c. C is 0 and d 0, so you have c bar and d bar. So So that's how you come up with this equation. So after we've made this equation, now the question does not say that just make the Boolean, make the truth table, the kernel map on the Boolean expression. They also want us to draw the logic circuit for this Boolean equation. Okay, so let me just rewrite the equation here. Let me say x equal to b c d bar, b c d bar, a bar, b bar, c d plus a bar, b bar, c bar, d bar plus a b c bar d plus a b bar c bar d bar. Okay, so to draw our circuit, what we are going to do is, so I have how many AND gates? 1, 2, 3, 4, 5. Okay, so I'll draw the buses here. Draw this. So we have A, Tenga B, then we are going to have C, so A bar, B bar, C bar, then we're going to insert a D for the cables or the buses. So we'll start with the first, this first AND gate here. This first AND gate is getting an input from B to start with. Okay, so it's connected there. It's getting an input from B, getting an input from C, getting an input from C, and also getting an input from D bar. Insert it like that. Okay, so this is an AND gate. The second AND gate is getting its input from A bar. Okay, this one is A bar, B bar. So A bar, B bar, then it has C and D. It has C, then it has D. Like this, another AND gate. Then the third AND gate that we have, the third AND gate is getting all the inputs from an inverted input. So we have A bar, B bar, we have C bar, and we have D bar. We have another AND gate, the third, then the fourth AND gate. The fourth AND gate has an inverted C bar here. Okay, so say A, B, and then C bar, and it has D. We have AND gate. Okay, so all of them are running into a plus, so that's an OR gate. All of these inputs are running into an OR gate. Gate is going to be X there. So this one runs there, this one runs there. Like this. Okay. So you can now say B, C, D bar, A bar, B bar, C, D. Okay, second, third, A bar, B bar, C bar, D bar, A, B, C bar, D. Then the fifth AND gate is going to come here. So the fifth AND gate is getting inputs like the third one. So it's everything has a bar. So A runs there, B runs there, C runs there, D runs there. So it is inserted there. Okay. It is A bar, B so it doesn't have an A bar. So actually connected from A. So it's A, B bar, C bar, and D bar. Okay. So that is how you're going to answer this question from June 2025, question 5 about the elevator size. So this is the truth table, this is the Carnot map, it's a Boolean expression, and this is the logic. This is the logic circuit.